Welcome to the 14th Cody Award public seminar. The Cody Award is an award for outstanding accomplishment in oceanography, marine biology, or earth science, and it rotates amongst those fields. The award itself is a medal, which you'll soon get to see, as well as a $10,000 cash prize. This award is made possible by a gift from Robert and Bettie Cody. Robert had a long-standing relationship with Scripps Oceanography. His great uncle was William Ritter, the founder of Scripps Institution of Oceanography and its first director. And so he had a long relationship with somebody that was deeply involved with the ocean and cared about it. And in addition to contribution from Robert and Bettie Cody, there was a substantial contribution from Capital Research and Management, an LA-based firm that Robert Cody had a long-standing relationship with. So that's how this award came to be and a little bit about it. The award winner is selected by a committee of Scripps faculty members and some external members. And this year's selection committee included Steve Candy, Ken Melville, and Mark Ullman. So a little bit about our award winner, Raffaele Ferrari. He is a distinguished physical oceanographer, and we are happy to welcome him back because he is a Scripps alum. And I learned last night that he actually had co-advisors here, which included Dan Rudnick and Bill Young. Thank you very much, Dan and Bill. He works primarily on ocean circulation and its interaction with the atmosphere and climate. He is a professor at MIT. He's the director of the MIT program in atmosphere, ocean, and climate. He also has a leading role in the MIT Woods Hole Joint Program, which is the academic program in oceanography jointly run by those two institutions. And he's also a lead in the MIT Climate Modeling Initiative. He has 2 PhDs, one here from Scripps and another one in fluid dynamics from the Polytechnic of Torino in Italy. He talked yesterday and gave a technical seminar on abyssal recipes, riffing off of Walter Monk's paper from the 60s by that title. And he's going to give a lecture that is a little less technical today. And so he's going to talk to us about ocean turbulence and climate. But before we turn to him for that lecture, Raffaele, would you please join me? And I would be delighted to present you with the Cody Award medal. Why don't we come over here, because I know they want to take it.
So thank you very much. At this point, I keep thanking, but sincerely, the committee and the selection committee, and I keep insisting that it's quite humbling to be here in front of, indeed, both my former advisors and a lot of people that inspired and taught me oceanography. I learned how to become a scientist during my 5 years here at Scripps, from 95 to 2000, and I've been inspired by most of the people in this room, so I hope you'll enjoy the lecture and you see the kind of work that I learned to do in places like Scripps. I think what I really learned coming here, especially coming from Italy, where I got my undergraduate degree, is to try to focus on working on exciting and relevant problems. So it's very easy to find either boring problems that nobody cares about or exciting problems that are not particularly relevant for anything. So to try to find that interesting balance where you're trying to move the science forward. And this is a bit what the theme of the talk will try to be. I thought I would really talk, as you heard, the award was given because of work I've done on ocean turbulence, and try to put that work in the context of why do we care about ocean turbulence and why it plays such an important role in the overall understanding of the role that the oceans play in the global climate system. So this will try to be quite informal and not particularly quantitative, so I try to give you fundamental ideas. The first one that I want to get through is why is the ocean important for climate, and I just highlight a couple of fundamental aspects of the role that the oceans play in climate, and then we'll try to address how turbulence affects both of these effects. The first one is that, as we all know, the ocean stores very large amounts of heat, and by doing that, it regulates temperature in the Earth system. Indeed, we know that temperature differences between the day and night on our planet are of the order of 10 to 20 degrees Fahrenheit, so they're pretty small. If you go to places that have neither an ocean nor an atmosphere like the moon, you're going to get temperature difference of hundreds of degrees. If you go to Mars that has an atmosphere and no oceans, again, the temperature differences between night and day are hundreds of degrees. You couldn't really live easily on a planet like that because you'd be scorching hot during the day, but too cold to get out of the house at night. The reason why the Earth has such a mild temperature difference between day and night is largely because the ocean is absorbing lots of heat during the day, and then it releases that heat at night. There is an atmosphere around that redistributes that heat over both sides of the Earth constantly, so the temperature differences are pretty limited. So it's the amount of heat that is stored in the ocean plays a big role in something as simple as the fact that day-night differences in temperature are not too large. Oops. When I say that the ocean contains a lot of heat, I mean especially compared to the atmosphere. So here I'm just showing how much heat is contained in the global ocean as a vertical column versus how much heat is contained in the atmosphere. It turns out that the ocean contains more than 1,000 times more heat than the atmosphere does. That's mostly because the ocean is more dense, contains more molecules per unit volume, and the heat is really the vibration of these molecules, so you have more molecules of water in the ocean than molecules of air in the atmosphere. So indeed, if you wanted to increase by 1 degree the temperature of the atmosphere, you need 1,000 less heat than to increase by 1 degree temperature the global ocean. So to show you that it's not that I'm putting out numbers to impress you, we can actually be a bit more specific in terms of what we think about climate over the last, 30, 40 years. So this is a plot from the IPCC report. I'm showing plots for the IPCC report not because the IPCC produces any new science, but they're very good at producing very nice plots based on science that is published before. So that's the role of the IPCC, to make nice plots that represent the science for the public. So this is a nice figure from the latest IPCC report, and what it's showing us is over time how much heat is taken by the various elements in the climate system. If you look at this blue wedge, this is the amount of heat that is absorbed in the upper 700 meters of the ocean. The darker blue wedge instead is the heat that is absorbed by the ocean between 700 meters and the ocean bottom. The reason why these two have been separated is that we have much more measurements in the upper ocean than we have in the lower ocean, so this is a better constrained estimate than the one down here. But then you can compare these two numbers compared to the amount of heat in this white wedge, is how much heat went into melting sea ice and land ice, or the wedge, this brown wedge down here, is how much heat has gone into warming up the land, the solid surface of the Earth. And then, if you really squint, you see that there is a little purple line down here. That is the amount of heat that went into the atmosphere. So that's a tiny residual compared to the amount of heat that enters in the ocean and the other elements of the climate system. You probably all read in the news big statements about the climate hiatus in the year between 2000 and 2010 or so. Statement that indeed the atmospheric temperature didn't rise as fast as might have been expected because of the increase of carbon dioxide in the atmosphere. You have to realize that the system overall, in the ocean, we don't see any evidence of heat slowing down or heat uptake slowing down. The reason why the atmosphere might have transient or periods where it doesn't warm as fast as we might expect is that it takes very little extra heat absorbed by the ocean to essentially damp any effect on the atmosphere. The ocean is such a large heat reservoir that tends to dominate the heat budget of the system. Getting more, it's something I want to point out because it will become relevant for what we discuss later on in the talk, is that if we can also look at where the heat is entering in the ocean. So all this heat, the largest amount, it's more than 90% of the heat that the Earth system is absorbing is entering into the ocean, and we can look at where it's actually entering. So this is depth, this is latitude. We go from low latitudes, in the equator, down to the South Pole, to the North Pole. Look at the vertical section, it goes only down to 2,000 meters because, as I said, we have better measurement in the upper ocean. It's very hard to see trends in temperature lower down. So if we look at what happens over the last 50 years, where you see red means that the ocean has been absorbing heat over time, and we see at low latitudes, meaning 30 degrees, within 30 degrees south and north, so San Diego latitudes and farther south, most of the heat is really absorbed pretty close to the ocean surface, the upper 100 meters or so. But if you look at high latitudes, you see plumes of heat entering deep in the ocean interior. These are the result at high latitudes. On average, the atmosphere is so cold that it cools the surface waters of the ocean to the point that they become very dense. Cold waters are denser than warm waters, and they sink all the way to the ocean bottom. This happens around Antarctica and mostly in the North Atlantic. Over the last 50 years, the temperature in the atmosphere, high latitude, are still cold, but they have warmed compared to what they used to be. This is what is called, it's a result of what we call global warming, but it tends to be amplified at higher latitudes, so the higher latitude has warmed even more than lower latitudes. So while it is true the water is still cold enough to sink in the abyss, they are not as cold as they used to be, so you see this warm anomaly. This water is a bit warmer than it used to be, that it sinks and entering the ocean interior from high latitudes. So that's where the heat is entering the ocean, and this is a large fraction, especially in the Southern Ocean. It's nearly 40% of the, well, actually I think it's 75% of the heat that is entering to the ocean seems to be entering through the Southern Ocean itself. The second way in which the ocean plays a fundamental role in climate change is through its impact on the carbon budget. So apart from heat, the ocean is a large reservoir of carbon. Again, we can look a bit at the partitioning of carbon between the various components of the Earth system. One is the atmosphere that stores, but this is not quite up to date, it's now 800 gigatons of carbon. We started at 600 or so gigatons of carbon before anthropogenic emission of fossil fuels, and now we brought the numbers up to close to 800 gigatons of carbon. Now you can compare this number with how much carbon is stored in plants over land. It's around 600 gigatons. But then you can compare the numbers to the ocean, which is 38,000 gigatons is stored in the ocean. It's much larger, it's 50 times larger than the amount that is stored in the atmosphere. It's a very large reservoir. Indeed, there are even larger reservoirs of carbon stored in the solid earth, in rocks. That carbon can be exchanged with the ocean, plant, land, and atmosphere, but on very long time scales typically. You're talking about hundreds of thousands of years, except for the recent period where we have been able, as humans, learn how to extract fossil fuels, burn it, and very quickly release some of the carbon reservoir from the Earth's crust. But otherwise, most of the exchanges are between the atmosphere and the plant and the ocean reservoirs on fast time scale, the time scale of climate that we're generally interested in. Again, we can start looking a bit at what happened now. We have time histories that go back to 1750, and in this plot we're looking at this green wedge is how much carbon has been emitted in the atmosphere primarily by burning fossil fuels. So you see how much this gray wedge is how much carbon has entered in the atmosphere over that time period. The brown line is instead how much carbon we use by changes in land use. So these are the two big sources of carbon that has been emitted, and then you can ask, well, these two are two positive sources, where did that carbon go? The total carbon in the Earth system has to be conserved. We're not losing that much to space. So we can partition where that carbon has gone, and well, one wedge is this blue wedge. That is how much entered in the ocean. We have this cyan color, that is how much carbon went into the atmosphere. These two are somewhat directly measured in the ocean, combination of models and direct observation. In the atmosphere, it is direct observations. And then the residual, this gray wedge, is instead how much ended up in the land surface. So you see again, the ocean might be over this last 150 years, 250 years, has absorbed close to 30% of the carbon that has been emitted in the system. Of course, if I could extrapolate this curve for another 1,000 years, most of the carbon eventually ends up in the ocean. But over this short time scale, the atmosphere is taking a bit more than a third, and the oceans another third. So again, the ocean is a large contributor to the uptake of the carbon that is being emitted in the system. We can again ask, where does that carbon go? And now I'm just showing the anthropogenic contribution of carbon. So the one that has been the results of the burning fossil fuels. Now this is a surface map. This is latitude from the equator to high latitudes and low latitudes. We have the various continents, Africa, Asia, and the Americas, where you have red and green colors mean that there is a lot of carbon that is going from the atmosphere into the ocean. The reason why this anthropogenic carbon is pushed into the ocean is that the exchange of carbon between the ocean and the atmosphere depends on the concentration of carbon dioxide in the atmosphere and the partial pressure of carbon dioxide, if you want the carbon dioxide in the ocean. The more you increase the amount in the atmosphere, the more you push some of the carbon into the ocean itself. And you see that the ocean, these large fluxes are entering into the Southern Ocean down here and in the North Atlantic. The primary reason for that is, as you all know, you store carbon dioxide more efficiently in cold waters, and these waters tend to be colder because they are at higher latitudes. That's why you keep your sparkling water in the fridge. It's the same statement here, so not much enters the low latitudes where the waters are warmer. There is a second important effect, which is ocean productivity. There is a lot of photosynthesis at high latitudes in the ocean, and photosynthesis stores carbon. Cells use carbon to build their cell material, so you're also taking up with production at these high latitudes. But again, it's important to note that much like the heat, there is a large uptake of carbon at high latitudes that supposedly sinks in the ocean interior. I cannot show you a map as nice as for the heat uptake for carbon because we don't have as detailed measurements. Jorge Sarmiento is leading now a large effort in the Southern Ocean where we're going to use a new generation of floats that profile vertically the ocean autonomously over years, and that should start giving us the first maps of carbon uptake in the Southern Ocean, but we don't have them yet. So far, just to give you a bit of a flavor, both uptake of heat and carbon in the ocean are leading all the contribution of the climate system and the changes in climate over the last few decades. So now how does turbulence enter in the story? Why is it that you need to know anything about ocean turbulence to address that question? And I think you can start here. This is a picture I've taken from the web. So this phone number, I don't know, maybe you can try to call it. It will probably try to sell you some coffee. But the main point here you see is that I've taken this movie, is that it's just a coffee cup, and if you don't like coffee, you can think about tea, that works as well. If you have a coffee cup in the morning and you want to put some milk or some sugar in it, you could just put the milk or the sugar and then just decide to wait for the two compounds to mix. We know that any fluid is composed of molecules that are continually agitated because they have some temperature, so the molecules of coffee would bounce against the molecules of milk or sugar, and over some times they would exchange their property and mix around. This is called Brownian motions. Eventually you would get nice mixtures of coffee and milk or coffee and sugar just by leaving the system evolve on its own, letting what is called molecular diffusion to act. Except if you compute how long it takes for that process to take place, well, for a regular sized cup it takes of the order of 10 days for the mixing to occur. So first of all, you would never make it to the office in time, or you have to drink your coffee without sugar, or more relevant, even in 10 days your coffee would evaporate, and so you would never really get to experience a mixture of coffee and milk. So what do you do? Maybe people can tell me, what do you do to accelerate that process? You stir it, right? So now what happens? So I put the sugar, and what happens when I stir it? I'm generating turbulence. It's turbulence that accelerates tremendously the rate at which the two properties are being mixed, to the point that you have to wait seconds, and the two mixture in coffee and milk gets very homogenized with each other. So as I said, I kept insisting that the uptake of heat and carbon is a fundamental property of the ocean in the climate system. And what you want to mix this heat and this carbon into the ocean, so having a turbulent ocean makes a big difference compared to a non-turbulent one, because the rate at which you mix those properties can be tremendously accelerated by the presence of turbulence. Now, in the ocean, the difference is that you don't have these big spoons acting around, so we have to understand where the turbulence comes from and how does it actually work. So first, we're going to look at a short movie. This is a snapshot of the sea surface of the global ocean. This is coming from an ocean model, but it's a model that is constrained, as we say, with observation. So it's a model that in some way is kept close to observe currents at the ocean surface. And the lines that you see, these white lines, they're some representation of the ocean currents at the surface. So you can start seeing the system moving around. So here we are on the eastern coast of the US. This is what is called the Gulf Stream current that probably people here at Scripps are very familiar with it. But what is important to see is that you don't see a big, nice, smooth current moving along the continent. You see that this current is always distorted and has a lot of swirls around the ocean. These are the equivalent of the cyclones and anticyclones that in the atmosphere we experience as weather. So these are instabilities of the main current. It's a bit like when you open the faucet and if you let very little water drip out, you get a very nice stream of water out of the faucet, but if you open it too hard, at some point it becomes very irregular. This is what is happening in the ocean, and these swirls of these cyclones and anticyclones you see here have sizes of more than 100 miles or so. So like distance between here and Los Angeles. In the atmosphere, the cyclone and anticyclone, because of the density of the atmosphere and property of the atmosphere, are much larger. A typical weather pattern has scales of thousands of miles or more the scale of the continental US. But it's essentially the same process. And you see that the whole ocean is populated by this kind of swirling motions, these cyclone and anticyclones that we tend to call macroturbulence from the Greek word macros, that means large. So it's large-scale turbulence. This is the large-scale turbulence that dominate the ocean. Globally, now, if we let the movie now should turn out around Antarctica, we're going to see what is called the Antarctic Synchropolar Current, the flow that flows all the way around Antarctica, and we'll stop there, but I just wanted to show you a second that that's a place where this turbulence is particularly strong. In the southern hemisphere around Antarctica, you have the roaring vortex of very strong winds around Antarctica. They try to accelerate a very fast current. And as a result, since it's such a fast current, this is the current that goes around the globe, around here. So this is Antarctica, this current around here. And you see that it's a combination of essentially cyclone and anticyclone. You barely see the current. It's all turbulence. So we'll see that in particular turbulence in the Southern Ocean, or macroturbulence in the Southern Ocean, is a very important element of the climate system itself. However, one of the issues with turbulence, we'll see in a second, is always that it doesn't act only at a particular scale. Turbulence is both exciting and difficult to deal with. That tends to excite motion on a whole range of scales. So now here I'm showing a section of the global ocean just to illustrate how turbulence seems to work in the global ocean. So this is latitude. This is a section in the Pacific collected as part of the World Ocean Circulation Experiment. This is depth, latitude. The equator is here in the middle, South Pole and North Pole. And what you see is very light density fluid over much denser density fluid. So the ocean is lighter at the surface and denser at the bottom. By the way, something that we all consider absolutely obvious, but I think it was Boyle, the chemist, that first pointed out that the ocean is probably stably stratified, meaning that denser water at the bottom and not at the top. Up to that point, people thought that since there is geothermal heating coming from the bottom of the ocean, probably the bottom of the ocean is warmer and lighter. At the time, people didn't realize if that was the case, probably the ocean would overturn very quickly and reinstate stable stratification. So even results like this that seem obvious nowadays have not always been the case. But now we know that the ocean is a set of layers of different density from the top down. As I said, there is this large-scale macroturbulence that mixes the ocean very effectively. So we have these large spoons that do mix the ocean, but that turbulence is very good at mixing along layers of constant density. So it's like if I'm mixing along this direction or where the layers tilt up, I can mix along this direction, but it's very ineffective at mixing across density layers. So one of the issues is that if water slides are being mixed into the interior, into the ocean interior, like in the Pacific down here, and they are in one of these layers, then there is no turbulence per se. The macroturbulence is not able to mix it back, to come back to the surface, mixing across this density surface here. It's a different form of turbulence that is very effective at doing that, and it's what we're going to call it microturbulence, from the Greek word micros for small turbulence, which is turbulence that acts at a much smaller scale than the macroturbulence we've seen before. And how does that turbulence arise? It's not instabilities of the large-scale current, or this large-scale current that generates cyclones and anticyclones. It's something happening at much smaller scales. Again, the ocean is a set of layers of different stratification. So this would be denser water, this is lighter water, and this is air. We all know that at the interface between the dense water and air itself, you can have surface gravity waves that people enjoy surfing out here and all day round. You can also have internal gravity waves, waves that are at the interface between layers of different density in the ocean interior. In the same way, these waves will move up and down. But like on the beach, if you look at your surface gravity waves in general, I mean, they're just moving water up and down. It doesn't look like they do much mixing, they just displace the interface. However, the waves, when they arrive on the beach, all of a sudden they break. During those events, there is mixing occurring. You're actually mixing water and air, or in some cases also water, air, and surfers all together. So there is an event that is catastrophic and does mix properties. And indeed, we can look at the numerical simulation to show how that event is happening, just to give you more an impression of this turbulence in scales much smaller than what we've seen before. This vertical scale is something order of 30 yards or so. This is the typical characteristic scale of an internal wave itself. And let's say this is a few hundred yards. We have a dense layer of fluid. There are a light layer of fluids, two of the layers that I've shown you before of the ocean. If I allow a wave to propagate along this interface, occasionally it can become so large that it breaks. It overturns and breaks much like a surface gravity wave, but now it's mixing light and dense fluids together, and now you have this green interface. So the small-scale turbulence process is very effective at mixing properties between the light and the dense fluid. So this is another form of turbulence, and we see that both are very important in setting the climate system in different ways, both the macro and the micro turbulence of the system. The fact that you have turbulence on this very large range of scales makes the problem both challenging and interesting. It's challenging because you can't really easily construct a simple numerical model, or even a theoretical model for that matter, that resolve all those cases. It means that if you wanted to tackle the problem with brute force, you need to have a numerical model that somehow has a representation of these small breaking gravity waves that have scales of, we said, tens of yards. And then if you want to resolve all the small scale mixing process that we've seen there, you're actually going down to inches, so you would need to represent every inch of the ocean for the small scale turbulence, but then you also want to resolve this macro turbulence at the scales of 100 miles, and then the full ocean circulation on thousands of miles. It's just that computer power is not strong enough to allow us to resolve all these processes at the same time. And this is really a characteristic of turbulence, the fact that there are motion on all range of scales and they all interact. And if you want to know how the global system evolves, you have somehow to grasp the interaction between all these scales. This is not a new concept, this is a picture. I'm Italian, so I go back to Leonardo da Vinci. I'm sure you can probably find a similar picture back in time. But this is that you have a flow of water into, let's say, a lake or whatever this is supposed to be. And what Leonardo da Vinci is trying to describe here is that, yes, you have large scale swirling motion, but then within this large scale swirl, there are smaller scale swirl and even smaller one. You generate motions on a whole range of scale, and this is what makes the problem very challenging, both at the time to explain what is happening and even today to predict, for example, how the full climate system evolves. This is a problem in the ocean as much as it is in the atmosphere. In the atmosphere, you probably hear a lot of discussion about representation of clouds in climate models, but that's small scale turbulence events that generate clustering of moisture and phase transition, and that's a hard part of the problem because I can't resolve every individual cloud and at the same time the full atmosphere with present computer power. In the same way, I cannot resolve every individual turbulent element in the ocean and at the same time the large scale ocean circulation. So now that I try to lay out a bit the two elements of the system I think are important. There is the ocean is an important element of the climate system, and there are these different forms of turbulence that seem to play an important role in mixing properties within the ocean in different ways. One mixes along layers of constant density, the other one, the microturbulence across layers of constant density. And I want to give you two examples that I think are quite tangible on how this process do really affect our understanding of climate on different time scales. So the first one will be based on the effect of macro turbulence in short-term climate, so future climate or climate on order of decades. The reason why macro turbulence, as I described, is like having a very large spoon of order of 100 miles or so. So it's effective at mixing properties on pretty short time scale, talk of order of tens of years. So it's affect climate on short time scales. We see that the microturbulence that tend to affect climate on much longer time scale, because it's like having a smaller spoon. It takes much more time. It's like when you're trying to mix your milk and coffee, you try to mix on the whole size of the cup if you can to accelerate the process. If you really mix only on a very small, tiny part of the domain, it takes much longer for the turbulence to really create full homogenization. So first, we look at the effect of macroturbulence in the problem that physical oceanography found quite challenging, interesting, and revealing of the scientific process of understanding changes in climate over the last 10 years or so. So here now I'm showing an idealized, well, it's an idealized, a sketch of the carbon distribution in the global ocean. We are looking from this is the surface of the global ocean. This is Antarctica on this side. This is the northern hemisphere, then towards the North Pole. And the colors are the concentration of carbon in the water. So the first thing that you want to see is that where it's blue means that there is little carbon. When it goes to yellow means that there is a lot of carbon. So the first pattern, this is depth, and this is latitude, and this is longitude. You see that there is much more carbon in the abyss of the ocean than at shallower depths. Most of the carbon is stored in the abyssal ocean again. First thing is that abyssal ocean is colder than the surface. The ocean is warm from the top, so it stores more, it dissolves more efficiently carbon. The second reason why this carbon reservoir is so rich, as we said, that there is production, there is photosynthesis at the top of the ocean that captures some carbon to build cell material, then this phytoplankton, the plants at the surface of the ocean, get eaten by higher trophic levels, like zooplankton and larger fishes that eventually die and sink and carry this carbon all the way to the ocean bottom where it's dissolved. So you have what is called the carbon pump that is very effective at taking carbon away from the atmosphere and storing it into the abyss. But more importantly, you really have this big gradient in carbon, high carbon down here and low values towards the surface. Now, to understand, we said that one of the major pathways to exchange of carbon between the ocean and the atmosphere is in the Southern Ocean. And we're going to look at what happens in, let's say, pre-industrial condition. This is the Southern Ocean again. There is this roaring forces that blow from left to right over the ocean surface. They're very strong winds that go all around the globe. It's the only ocean that is strictly, that goes all around the globe uninterrupted by continents. We are on a rotating Earth, so it turns out if I have a wind going from left to right, the wind tends to push at least the surface water a bit to the left. So it's pushing water out of the Southern Ocean to lower latitude, towards the equator. So it's a bit like you have your bathtub and there is some force that keeps pushing water out of the bathtub. This is this strong roaring force at the surface of the ocean. Since you're pushing water out of the bathtub, well, some water from the deep bathtub must be coming out to resupply this water that keeps flowing out. In the ocean, then there is water in the abyss that comes in. So essentially you have a circulation. Water coming in is sucked up by the winds and pushed to lower latitudes. But since, as we said, there is all this high carbon in the abyss, these winds essentially bring carbon-rich water towards the surface. And indeed, in pre-industrial condition, the result was that the carbon concentration in the Southern Ocean, you see that they tend to the green, they're not really blue, they tend to be a bit higher than they would without the wind. So a lot of the carbon in the ocean was fluxed back into the atmosphere. The Southern Ocean was the source of carbon for the atmosphere. Now we corrected that because by putting so much carbon in the atmosphere, now the amount of carbon in the atmosphere is large enough that we have more carbon in the atmosphere than in the Southern Ocean, so we're pushing it back. So now the Southern Ocean has become a sink of carbon. But, and this is a nice detective story in a sense, as we'll see in a second, a paper, this is again, it's an update of an estimate of how the winds, the strength of the roaring forties has changed since 1950 to 2010. But the first paper that actually raised the issue was published by Susan Solomon, a scientist at the time at NCAR, this is the National Center for Atmospheric Research. What they noticed is that if you look starting from the 70s or so, the strength of these winds has increased. So it started going up. The increase is close to 20%. It appears that the increase has something to do with the depletion of ozone around Antarctica. These are the winds that flow around Antarctica. And that decreases because of chlorofluorocarbons emissions in the stratosphere. This is actually, if you want, it's the most glaring example of an anthropogenic effect on the mean state of the atmosphere. That's a big change, that increase in winds, and it's indeed the result of us tampering with the climate system. But interestingly enough, if you see these winds increasing, as soon as the paper came out, another scientist, Corinne Leclerc at the University of East Anglia, who is a biogeochemist, meaning somebody that studies the carbon budget of the ocean, realized that, well, I know that carbon is continuously brought up toward the surface, but the rolling fork is in the Southern Ocean. If the winds are strengthening, probably I'm bringing more carbon up towards the surface because the amount of water that I keep bringing up is proportional to the strength of those winds. That would mean that I'm fluxing more carbon out of the atmosphere than out of the ocean than I used to do. Right? So we said that the carbon in the net is entering into the ocean, but now I'm also returning a lot back. So now this is a picture that became quite canonical in 2007. It was a Nature paper. The red line is the flux of carbon out from the atmosphere into the ocean if the winds had remained constant. So they just do an estimate. The fact that this curve becomes more and more negative, it's just telling you that the flux of carbon into the ocean is increasing faster and faster. This is if the winds had remained constant. But now what Corinne Leclerc and colleagues estimated is that they actually show these other curves, a different way of estimating how much carbon is entering into the ocean. And what they noticed is that the flux of carbon from the atmosphere into the ocean didn't keep increasing in response to the carbon dioxide concentration in the atmosphere, which we know are happening because of estimates like the Keeling curve. Looks like after a while, this curve just flattened out. It didn't keep absorbing carbon. So the ocean seemed to have stopped absorbing all that carbon. And you said, well, that's very consistent with the idea that maybe the winds are increasing and they're returning a lot of that carbon back to the atmosphere. Indeed, what she did, she took a climate model, so a large-scale model that tries to represent the circulation of the oceans. This is again the red curve, is the same red curve that we had up here. This is how much the flux of carbon from the atmosphere into the ocean is increasing over time. It's becoming more and more negative as we progress over time, as more and more carbon dioxide entering the atmosphere. But the blue line instead is the prediction of the climate model with a change in the strength of the wind. So you see for a while the winds are not changing, and indeed the blue curve more or less follows the red curve. There is some wiggling because the winds do keep changing, they have natural variability, but after a while it seems to flatten out. And that again, it's a signature that you're increasing the wind, so a lot of the carbon that the atmosphere is pushing into the ocean is returned back by these currents coming towards the surface. So these pictures seem very consistent with the picture above, and everybody insisted that this is actually bad news because it means that the ocean were taking up 30% of the carbon, anthropogenic carbon we were emitting in the atmosphere. The Southern Ocean absorbed 40% of that, and now all of a sudden it seems to be stopping taking up that carbon dioxide. So the projection was that the atmosphere concentration of carbon dioxide would go up much faster than had been predicted. But in some sense, I find that it's a good news. If people ever hear about conspiracy theories about climate change, I think this is a good example to see how science actually operates. If you have an idea or somebody come up with an interesting paper, the first thing is that everybody in the scientific community tries to see whether they can turn it down. You get much more recognition about proving everybody else wrong than just following common wisdom, because that's the way you establish your name, that's the way you can actually get grants because you're doing something different from everybody else. Indeed, the dynamicists started trying to understand whether the story that was presented was consistent with what they knew. In the picture I described you before, there was all this current of these waters brought up to the surface. I never mentioned turbulence, but we said that turbulence is an important aspect of how you mix property into the ocean interior. So now I just want to show you a simple simulation. The reason why turbulence was not entering into discussion is that all the analysis done before was based on climate models that cannot resolve all these small swirls generated by the macro turbulence in the global ocean. The models are just not powerful enough to resolve all that small scale dynamics. So I just want to show you, however, we can resolve the macro turbulence in idealized and smaller versions of the global Earth. And this is an example run by a student at MIT, Ryan Bernat, in 2012. It's a nice movie. So this is an idealization of our Southern Ocean. Antarctica would be here. Let's say the South America is up there. And this is our sector of the Southern Ocean. We're just looking at a small patch of it. And these layers of different color are the different layers of the ocean, starting from layers and getting denser and denser towards the bottom. So this is the full depth of the ocean. And what we're going to do now, we start with no winds and we start accelerating the winds. So we know that for a while, since we have winds blowing at the surface of this ocean, waters will be brought up. and pushed towards the equator. But we'll see in a second that something else happens that you might have anticipated. So first, don't worry about the arrows, but now you see these particles are the winds blowing at the surface of the ocean. I'm pushing water up. Here you see that I'm squeezing the warm waters, and then I'm pushing it out of the domain. Now what you see is that the system goes, what we say, unstable. You generate a lot of that macroturbulence I was discussing about before. That should be something that, or at least it's something that got the theoretical community very interested, because we know that turbulence is very effective at mixing properties back into the ocean, so it might be quite relevant for the story of the carbon take, and had been ignored in all that discussion, but the turbulence is quite vigorous when you let the system develop. So what could be done for this problem is that there have been a number of works, some of which have been involved, some of which Ryan Abernathy, a student at MIT, has also worked, Paola Cecil here. I mean, there's been a very large effort from the community trying to understand in detail the dynamics of this system. So in particular, for example, here, let's assume that again we are playing with this toy model that I've shown you before, where we can actually resolve the macroturbulence itself, that we generally cannot. And we are looking how much water is transported towards the surface of the ocean for different winds. So we keep increasing the wind to see what happens. These black dots is how much water is brought up towards the surface if there was no macroturbulence in the ocean. So this is what the climate model would predict. And you see, as you increase the wind, the amount of water you transport to the surface keep increasing quite rapidly. As we said, this is what indeed what the climate model would predict, and was the insight of Corinne Le Carré's work. However, now look at this is what actually happens in that simple toy model. This, don't worry about the difference between the red and the blue dots. It's two slightly different configuration of the model, just to test whether the model is self-consistent. But you see that the slope of this curve is much less than that one. It's telling you that the amount of water you bring up in response to the increase of the wind stress is not as large as you might have expected in the absence of turbulence. And it's because the turbulence is mixing a lot of the properties that you're trying to bring up back into the abyssal ocean. So it's just acting against what you've done. Now you're adding an extra stirring that wants to mix the surface water with the abyss. Indeed, this shading gray is about the range of change in the winds that we have observed in the historical record over the last 30 years or so. So there was in the absence of turbulence, you would see some difference. A bit more water was coming to the surface, and that's what was bringing some of the carbon back to the atmosphere. But when you look at this simulation here, the change is very minute. So now you have a problem. The dynamicists in the community are really insisting that you shouldn't observe much of a change in carbon uptake in response of a change in surface winds, except that we are earth scientists, and Corinne Le Carré had actually used real analysis. He had actually used real observation of carbon dioxide in the atmosphere, and that really seems to suggest that the carbon was uptaken at a much slower rate. So now you had a discussion that maybe she's not interpreting the result correctly, or maybe the dynamicists are missing something fundamental about the carbon system. Or maybe you just wait a few more years, and this is a revision of the previous work. It's Land Schutzer et al. It's actually a postdoc that was working in Corinne Le Carré's group, except that he published this work without her name on it, so you conclude what you want out of that. But it's again an update of the previous blog, just the colors are a bit different. The previous blog, Corinne Le Carré published her work in 2007 using data up to 2005. The black curve that is sloping down, this thick black curve, is again the flux of carbon from the atmosphere into the ocean, assuming that winds remain constant. So that was the red curve in the previous plot. So you see that it should keep increasing. So there is more and more carbon getting into the ocean because the carbon dioxide concentration in the atmosphere are going up because of fossil fuel emission. But now this is the estimate of carbon fluxes from the atmosphere into the ocean. And now you see that the curve, these are different approaches to the estimate. In particular, the blue one is quite different. It uses a neutral network, so let's forget about the blue one because there are discussions whether it's done consistently with the previous work or not. But if you look at the black and red ones, you see that indeed they oscillate. This is the time when the winds weren't really changing. This is when the wind starts accelerating, and you see that there is this flattening when we said, well, as long as the curve goes down, it means that there is more and more carbon getting into the ocean, but now all of a sudden it flattens, meaning that the flux doesn't go up anymore, even though the carbon dioxide concentration go up. But then you see after 2005, it seems to come back, so it recovers and goes back to exactly what you would have predicted in the absence of a change. in absence of a change in net carbon uptake, in the sense that the change in circulation don't seem to have affected the change up to 2010. The system went back to what it should have been if there had been no change in the wind per se. So that is suggesting that indeed for a while you have this stalling of the system because you are accelerating the wind. So for a while the turbulence you've seen also in the simulation I've shown you, it takes a while before the turbulence develops. So for a while indeed the winds were effectively bringing excess carbon to the surface, not allowing the ocean to absorb as much as it used to. But then after a while the turbulence develops and starts mixing back properties into the interior, so that was just a transient effect. And I find that this is a nice and reassuring example where people went and looked at the dynamics, convinced themselves that they didn't understand something, and they wait until the data seem to either reject or support their understanding of the dynamics, and now we are at the point we think really what is happening in that system. There is a phase, there has been a short transition of a few years when the carbon uptake in the ocean was reduced, but now it seems to have recovered. Don't have any time, do you know what's the time? Okay, good. So the second example that I want to show, so this was a good example where macroturbulence is affecting the response of the system on time scale of 5 to 10 years. Now, if you want to see how microturbulence, the small-scale turbulence, affect the climate system, you have to go much longer time scale just because it's a less efficient form of turbulence. It takes much longer to mix properties. A bit like I said, molecular mixing of a coffee cup takes of order of 10 days, but more efficient forms of turbulence might take of order of a second. Microturbulence takes years. They generally affects the climate system or the ocean system on time scale of thousands of years, while macroturbulence is more on tens of years. So if we want to see the microturbulence affecting the climate system, we have to look at climates on very different time scales. So now we're going to compare present climate versus ice age climates, in particular the last ice age. So now we have something of the order of 20,000 years to look across, and that's a time scale over which microturbulence can have a profound impact on the climate system. So just to show you what is, well, we know the ice ages really existed, we can measure them quite directly. This is a time history of the temperature in Vostok or Vostok. My wife is Russian, so she gets very upset every time I say Vostok. It's apparently Vostok. It's a Russian core. What scientists do, they take long cores of ice from Antarctica. The deeper you go in the ice, the back you go in time. It's ice that was formed a long time ago, so you can time that. You can get the timing of the ice, and there are little bubbles trapped in the ice that preserve the properties of the air when it was last formed. So we can look at temperature excursion in those air bubbles. So we start, this is present day, and you go backward in time, going to the right. This is an interglacial period, our period, and you see the temperature plummeting. You're entering an ice age. The temperature dropped by nearly 10 degrees. Here you're at high latitudes. Temperature change at high latitudes are much larger than mid latitudes. The mean temperature change between the present day climate and the glacial climate is sort of between 4 or 5 degrees, but at high latitude is close to 10 degrees. We are in an ice age period. This is the maximum of the ice age, called the last glacial maximum. Then the temperature after 100,000 years here comes back up. So you have another interglacial warm period like the one we're living in, but then you plummet in another ice age, and you keep repeating this pattern in temperature. So the temperature really changes over hundreds of thousands of years. As the temperature is changing, so the climate is dramatically changing, you also see carbon dioxide is coming down. You're in an interglacial climate. This is like a present day climate. These are carbon dioxide concentration of order of 280 parts per million, or if you wanted something close to what is it, 500 gigatons in the numbers I was giving you before. Then the amount of carbon in the atmosphere all of a sudden decreases by 30% as you enter in an ice ages, then it comes back. In the next interglacial, then you get colder, the carbon drops again, you're warm, the carbon comes back up, and so also the carbon dioxide concentration in the atmosphere are swinging back and forth of hundreds of thousands of years, much in synchrony with temperature. There is a lot that one could discuss about this curve. It's a very important element of the climate system we are trying to understand, because indeed it tells us something about the connection between carbon dioxide and temperature. Here, I want to focus on one particular aspect that is puzzling us, is that 30% of the carbon dioxide in the atmosphere has disappeared, and we want to know where it ended up. We know that it's likely not to have ended up in land because in a much colder and drier climate, if anything, vegetation would decrease, so you lose carbon from the atmosphere. There are from land, from plants, so there are direct lines of evidence that indeed the storage of carbon on land has decreased. So that leaves essentially the ocean as the major candidate for taking up that excess carbon. So we want to see whether there is any evidence that that could have happened, and in particular is these ice age periods are very long. They are 100,000 years long, so you have to store that carbon in the abyss in the ocean somehow for a very long time. If I try to put carbon in the ocean and reduce it in the atmosphere, the first thing that happens is that if I just put it at the surface of the ocean, it just wants to flux back into the atmosphere. If I create a big difference in carbon dioxide between the ocean and the atmosphere, it's what we're doing now. If you increase the carbon dioxide in the atmosphere, well, it all just wants to go back into the ocean. If you decrease it in the atmosphere, well, it would all want to come back from the ocean to the atmosphere. So the first thing you can do is actually see whether something happened in the ocean quite dramatic between the present day and the last glacial period, to get some insight that maybe helps you to understand what is happening. Here I'm looking at a section of a tracer that is called delta C13. This is an isotopic ratio of carbon. It doesn't matter what it is specifically. You can just consider it as a dye that you can measure everywhere in the ocean, both in present climate, and I'll explain in a second how we do it in past climate. So it's a very useful tracer because we can also measure it in past climates. So this is for the present day climate, and we're looking at a section in the North Atlantic. So this is depth. This is around Antarctica, about 60 degrees south, and all the way to the 70 degrees north, close to in the Nordic seas. But you see there is this yellow, there is light values of delta C13, so a yellow color in the Southern Ocean. This is the water that sinks around Antarctica that we keep discussing, that it's entering, and it sits below 4,000 meters or so in the global ocean. We also see a plume of reddish color. This is larger values in delta C13. It's just another dye that comes from the northern hemisphere. It's mostly in the north Atlantic, sinks again in the abyss and fills the ocean from the other side. Now what we can do is that we can make the same map for the last glacial maximum. The way you do it is that you drill cores again in this kind at ocean bottoming, the sediments at the ocean bottom again. You take a deep core, and the farther down you go into the ground, the farther back you're looking in time. It's deposited or deposited farther back in time. And delta C13 is a property that is conserved in the shell of organism, living organism at the time. So you can still measure what the value of delta C13 was at the time when this organism died. And so you can, by looking at different cores and different margins in the ocean, you can reconstruct a map of delta C13 also for the last glacial maximum, a particular point in time. And this is the map you see. What is important for us is that now, if I want to see where the carbon is coming from in the Southern Ocean, this delta C13 is coming from, you now see that there is a plume that comes from the Southern Ocean and essentially fills the whole ocean up to 2,000 meters. So it looks like the volume of water that comes from the Southern Ocean, it's everything below 2,000 meters. What comes from the North Atlantic is up here, it's just confined to the upper 2,000 meters. There's been a big rearrangement of water masses for whatever reason. In work that we've done, you can show that the reason why this change in volume seems to be happening is very much connected to the fact that you had an expansion of sea ice at the surface of the ocean. You're entering in an ice age. Here I'm not discussing, we could have fun and discuss it, but I'm not discussing how you enter in the ice age. But when you enter in an ice age and you form more sea ice, you expand the volume of this water that forms around Antarctica. Nowadays we have very little sea ice, so the amount of water you form around Antarctica is a very small fraction of the volume of the North Atlantic, but it becomes much larger when you enter in an ice age climate. I'm pretty much done. So now, how does microturbulence enter in this story? Well, as we discussed, microturbulence is the result of internal waves, this oscillation between between layers of different densities in the ocean. And those are generated because you have flows over the ocean bottom that displace this interface. So you have currents on the ocean bottom and it goes over a seamount. When this current goes over the seamount, it displaces this density serpent and they start oscillating. The higher the mountain, the more they oscillate and they can break and generate turbulence. It turns out that most of the ridges, seamounts, and strong irregularities in bottom ocean topography are below 2,000 meters or so. So most of this very strong internal gravity wave field and mixing this microturbulence is confined to below 2,000 meters. It drops quite substantially when you move about 2,000 meters. That's something we do see in the present day ocean. So can we put this in the context of the picture I've shown you before? Now these purple arrows are representing where mixing is occurring, and I'm just trying to draw arrows below 2,000 meters where most of that microtubule is actually happening. So what you see here is that you have these plumes of water. These are the plumes of water forms around Antarctica at high latitude that sinks in the ocean abyss. These are waters that are rich in carbon. You remember, these are waters that are very cold in regions that are productive, so they are rich in carbon. They bring carbon all the way to the ocean abyss. But now you have all these plumes that tend to mix all this rich carbon back to the surface. They keep mixing it up, both in Antarctica, this plume of dense water from around Antarctica, and these upper plumes that come from the North Atlantic. Like you're putting, let's say, your coffee up here, and then this is your coffee, and at the surface is where you put your milk while you're mixing very effectively the coffee all the way back to the surface. So the carbon will never sit there for a very long time. However, something quite different happens when you enter in a glacial climate, because as we said, the volume of water in the southern hemisphere now expand all the way up to 2,000 meters. So now it's like, here you have your coffee, below 2,000 meters, this is the carbon-rich water that formed around Antarctica, and on top of it you have your milk. Now you're only mixing where there is coffee, you're never mixing the coffee with milk, so the coffee remains at the bottom, it never comes back to the surface. You might think, well, but it's still in contact with the atmosphere up here. Well, it turns out that this is where you're under ice, so it just doesn't ventilate that much either. So all of a sudden, just because of how microturbulence can affect the fluxing of carbon out of the system, you can dramatically decrease the amount of carbon dioxide in the atmosphere. So this is an active feedback. You start an ice age. As the ice age progresses, you take more and more carbon out of the atmosphere that is stored in the abyss and lost for a very long time. As the carbon dioxide in the atmosphere drops, the system gets even colder, so the sea ice expands even more, and the system precipitates in this very cold climate state. And it will not get out of it until the orbital forcing of the system starts melting the ice. You need a redistribution of the solar forcing to melt some of the ice, and that takes about 100,000 years, in particular over the last few ice age cycles. So to conclude, I think that I try to illustrate that the ocean is clearly a key component of the climate system, in particular through its storage of heat and carbon, and how effectively you mix heat and carbon in the ocean is very sensitive to the turbulence in the ocean itself, because turbulence is what accelerates mixing of properties in a fluid, and there are both macro turbulence that help affecting climate on decadal timescale, on 10 years kind of timescale. This is a very fast process by oceanic standards, not by human life standards, but that's a fast system. It's a climate change that we can experience. It also that affects climate, this turbulence also affects climates on much longer time scales through its microturbulence, whatever stores carbon in the deep ocean or heat in the very deep ocean. And I find that the big lesson is that that is true for anything you hear when you want to understand why is it so hard to predict changes in the climate system. It always comes back to the fact that fluids like the ocean and the atmosphere are strongly turbulent, which makes the problem both interesting and challenging in the sense that there are scales on all range of different dimensions, from inches all the way to thousands of miles, that are acting together. So it's a bit like having a system where there are so many components and you can't represent each one individually. So the way we're making progress is not by trying to simulate the full system at once or have models that try to represent everything at once, because when you try to do that, you always have to stop at some point and ignore part of the question, and you don't know whether that part that you ignore is relevant or not. So the way you make progress with ideas like this, where you go back to your fundamental understanding of the system, you can either play with toy systems, like the one I've shown you, to understand carbon uptake in recent climate change, and to see whether your fundamental understanding suggests that turbulence is an important part of the system or not. If it is, you try to understand what that effect is, and then you can go back to your large-scale climate model and represent the effect of turbulence that you understood. Or you try to use more your fundamental understanding of changes in global climate and try to see whether, again, you can explain observation of paleoclimate, see whether they are consistent with your understanding of the present-day turbulence. Thank you. Questions? Yeah.
You notice on the graph, where we're at right now, there's a really fast increase of carbon. But every 10,000 years,
No.
there seemed to be a very fast increase of carbon.
You mean that this is much?
40,000 years ago?
You mean this
Right.
versus that?
The blue.
Oh, the blue is temperature.
Okay. Okay, the CO2. Right, but the spike is straight up on us.
So we're going in this direction. So yes, here I'm entering into an ice age, and here I'm coming out of an ice age. It's very asymmetric. It's absolutely true that it's not a simple smooth curve. And now this is the question of how do I initiate an ice age versus how I decrease, or how do I come out of an ice age. It's a very asymmetric system. I'm happy to talk about it afterwards. It has to do with orbital forcing and the fact that you're trying to go from a stable, your transition between two different very stable systems. So the time you're perturbing from one and you follow into the other, but you lose, there is a way that you lose a lot of the carbon on a very short time scale, but then it takes a long time to ramp back up because one process is faster than the other. And this is where the mixing comes in. One element is very slow, the other one is faster.
Thank you.
Thank you. More questions? Yeah.
I just wondered if you can clarify something about your Del 13 graph, the plot that showed as a function of latitude and water depth with the Del 13. So I just was understanding how they reconstruct the depth.
So the way it's done is that you take cores along continental margin, and you can do that at different depths. You just have a continental margin. So what you're really always seeing is the local bottom delta C13 value, but since a particular ridge will have, you can take cores at different depths. You can reconstruct a whole point. You cannot do it at every point. I don't know if from there you can see, but there are white dots in this picture. The white dots is whatever depths they could take a core, because they also have to look for particular places along the margin where the accumulation rate of the sediment is fast enough that they have a good preserved record. If it's very slow, you can't distinguish different climate states. And so they just go along these margins from the top of the ocean all the way down, and they reconstruct some vertical structure of the ocean. But it is an important consideration in this map that people keep thinking about. While in the present day ocean, you really have a three-dimensional view. You sample that tracer everywhere, including the ocean interior. Here, you're always looking very close to the ocean bottom, what the value was, and then you're assuming that that is representative of the value at that level everywhere in the ocean. Yes?
I'm jealous, so I'm thinking about from the billion year scale, geological scale, that with the movement of the continent position to the other, say, either macro, turbulence.
So, yeah. On the timescale I'm talking about here, the continents don't move, but already there is one thing that does change, and there's been a lot of discussion on how it affects microtubulance in particular, is that you are forming lots of ice, so you're taking away a lot of water from the ocean and storing it on land in the form of ice, so the sea level drops by around 140 meters at the last glacial maximum. So now a lot of the shelf doesn't have water anymore. It turns out that these microturbulence, these gravity waves, dissipate a lot of their energy. A lot of the breaking, much like surface gravity waves, happens when they are very close to the shelf in the present day climate. Now all of a sudden, those waves cannot break there. They might break more in the ocean interior, so there have been people, including Walter Monk here at Scripps, that have suggested that maybe microturbulence was much more energetic in the deep ocean in past climates. You can ask whether that might have had an impact. If you go farther back in time, and we're talking about now very different climatic configuration, there is a lot of discussion, for example, that the macroturbulence might have been very different when Drake Passage was closed. So now we're going back to, I don't know, what is it, 50 million years? So in that case, all of a sudden you don't have a circumpolar current like we do today, and that is a big source of macroturbulence in the ocean today. Now all of a sudden you're shutting off that system. And so the transport of heat and carbon across from depth to the surface and across different latitude was very different. That probably has impacted quite dramatically the climate of those states. So yes, the answer is that both the mean state and the turbulence would have changed a lot of different continental configurations in ways that would impact the climate. Yeah.
Turbulence
worlds have smaller worlds that cheat on their velocity, and small worlds have lesser worlds that go on to viscosity.
Yeah.
So as temperature changes, viscosity changes, and it's well known that wind stress is directly related to these very small length scales within velocity to viscosity. What are your thoughts on changing viscosity with global temperature?
So what you're changing is the molecular viscosity, and we're talking about very small temperature changes in the ocean, right? I mean, we're talking about approximately a degree temperature change in the atmosphere, but in the ocean you're talking about 0.1 degree temperature change, 0.2. So
degree Kelvin change, the viscosity change about 0.02%.
yeah,
Very small,
but you're much smaller than that in the ocean. The amount of temperature change in the ocean, just because it has this big heat capacity, ends up being a very small temperature difference for the time being. You're talking about a fraction of a degree, so the change is very small. But more importantly, I think that what mixes, probably was going back to the statement I made, what mixes heat and carbon into the ocean eventually is not molecular processes, this turbulence. So it's what we would call a turbulent viscosity or a turbulent diffusivities, and those don't necessarily depend on temperature as directly like as the molecular process. So if I run a numerical experiment using different fluids with different molecular viscosities or diffusivities, as long as the micro and micro turbulence is the same as what I observed today, the rate of transfer would remain the same. Yeah, I would think so. Anymore, I said that you're all very inquisitive. Rick.
Just a general thought. Carbon is a very passive tracer, and temperature is a very active one. How much does that figure into all? Do people even think about it that way?
Oh, absolutely. And that's something I completely omitted. It turns out that it's interesting that we know the rate of carbon uptake in the ocean, I think, much more accurately than heat uptake, mostly because it's a passive component of the system. So as long as you know the present day circulation, you can infer that if you know what is the change in surface carbon concentration in the atmosphere, and if the circulation changes a bit because of changes in winds in the Southern Ocean, this is all you really need to know. You can just project it. It's a passive tracer. It's just affected in the interior. All you need to add to it is knowledge of chemistry, because the ocean is passive in the sense it doesn't affect the dynamics, but it's very active chemically. But once you know that, you can project the carbon uptake quite accurately. The heat uptake is much more uncertain because as you start taking up more and more heat, you tend to change the circulation of the Southern Ocean. And those effects tend to be leading order much more directly on a faster time scale than for the carbon uptake per se. So it's quite embarrassing that I didn't discuss much ocean heat uptake, because our estimate on ocean heat uptake for the most part are based on numerical models that we trust up to a certain point, at least at the level of accuracy we would need to see that little change in temperature you see in the ocean interior, where we can do better with carbon uptake, even though our carbon models are definitely much less sophisticated and grounded in basic physics and chemistry than our dynamical model, but just because being a passive tracer is a much simpler problem. So absolutely, it does feed back, and those changes in the circulation because of changes in temperatures are important. Ben?
So you mentioned that turbulence is a very old problem, and it's one of the maybe the most important unsolved problem in classical physics. It keeps us all in business, so we all have something to do. But you've kind of given a great broad overview of how turbulence is important for climate. But if you could choose one aspect of the turbulence problem to solve, to come up with better forecasts of the climate, what would you choose as the problem of turbulence to solve?
In terms of what problem we want to solve, I think as a society, it's much more macroturbulence what dominates transport on shorter time scale. There is no question about that. In terms of whether it is a fundamental open question in physics, well, I would say fluid dynamics, because physicists, I'm sure, would come up with a much longer list of other problems that we are not aware of. But even in fluid dynamics, I think that what we are asking is quite different from what the classical fluid dynamicist thinks of turbulence. What we are asking is how the turbulence is affecting the mean system, the mean climate system. We don't want to know properties of turbulence. There are number of theories that already tell us some fundamental properties of turbulence. It's just that people want to know much more than the leading order description people like Kolmogorov has produced in the 40s of last century. So my impression is that we're making quite a bit of progress in understanding some of the feedback with what I call, for example, the macroturbulence and the mean state, and progress is being made, and we stand chances to actually being able to predict those interactions. It doesn't mean that we have solved the turbulence problem, because we solved a very specific element of turbulence and how it affects the mean state, not necessarily all the properties of turbulence in the system. Turns out that a lot of the properties of turbulence, of the macroturbulence in affecting the circulation in the Southern Ocean can be understood from quasi-linear theory, so simple models that don't even resolve the full turbulence, but just look a bit how these worlds are generated by simple instabilities of the mean current. So I find that there is actually quite a bit of promise, at least to answering those questions. And it might not be as hard. We don't have anything, for example, so from the ocean perspective, that would be the question. I find in the atmosphere, they have a much tougher problem. For example, for them, the obvious question to address, in a sense, from the turbulence perspective, is formation of clouds. That involves all phase changes and microphysical clouds, which is much harder because it's something that we know less about. They're very difficult to measure. And that's more of a problem, and I don't think it's just turbulence theory that will get you there. At least in our case, that's what it is, and probably, I mean, we are making progress. I find that the example I've shown is a striking example of people actually understanding how the turbulent response acted and why what we were observing, the observation wasn't quite what we should have expected, and it was the theory that helped us to go back and revisit the observation and understand what was actually happening. So it's a good example where there was enough theory to understand it.
So you make this neat distinction between macro and micro business, right? But there's meso business, and so does that make life a little bit more difficult?
Well, absolutely. I think I focus on those two aspects because they are the rate controlling process, or they are the spoons that are most effective at mixing properties. The macroturbulence, a long density surface, and the microturbulence, a cross density surfaces. But the story is not quite all there, so when you talk about what is now a hot topic, at least in the field of physical oceanography, is that much like in the atmosphere, you can generate cyclone and anticyclones, but when you look at the weather forecast, you care up to a certain point whether there is a high or a low pressure system passing over your head. You're more interested in the fronts that pass there because those are the ones that have big rainfalls associated with them and dramatic changes in weather. The same thing, these fronts do occur also in the ocean. They form on the edges of the cyclone and anticyclone. Those that dominate a bit the vertical exchange of properties between the surface of the ocean and the interior. So that adds to the complication. That's what I call the turbulence problem. Now, it depends on the specific question you have. And now there are scales of turbulence motion and all scales you can think about, and they all matter for some aspects of the problem. So here I've chosen two problems where those two classes of turbulence were dominant, but you can find plenty where other classes are relevant. And indeed, if you want a full theory of climate, eventually you need to account for all of that. Should we stop here?